All right, so taking a look in this section for 0.6, we're going to start with something that I think is kind of misunderstood by a lot of students when we're doing Algebra 1, okay? And that's mostly because when you look at square roots, if I were to ask you what squared equals 9, what would you say? 3 and negative 3. That there are two options to this. And so when I come along and then I say, what's the square root of 9? What would you say? 3. And is anybody tempted to say negative 3? Sometimes, maybe a little tempted. The idea is that when we're talking about radicals, we have to designate whether we really want to have the positive one or the negative one. And so what we're going to do is we're going to come in here and we're going to talk about what is called the principal square root. The principal square root, whenever I talk about that, is specifically only doing the positive one, principal positive. So that's why I want you to kind of underscore in your notes that this is talking about a non-negative real number b. Non-negative. What does non-negative mean? It could be 0 or positive, okay? 0 or positive. So if I have a real number b that is either 0 or positive, then it's going to be called the principal square root as long as b is the square root of a, which is really only true if b squared equals a, okay? And yes, there are two square roots to a. But if I just write square root of a, that's always assumed to be the positive one, and that's the only one I want you to tell me, okay? When you are looking at it, if I want the negative one, take a look at the difference. If I want the negative one, what do I put in front of it? A big old negative sign. I'll tell you I want the negative one, okay? So that's why that this is the principal, and then this is the negative one, the other one that's there. And typically when we're doing square roots, we always go with it's the principal one, so we remember that we're dealing with the positive one. All right, now the parts of your square root, the a, that's underneath here, is called the radicand. Because what's the sign, the square root sign called? The radical. So we figured we'll make the radicand, the thing underneath, be related to radical. All right. And then, of course, b is going to be your principal square root. Principal root. Which really just means, hey, it's the positive one. Now, you've done radicals before in algebra class, so you should be enough versed, especially now that I've said just give me the positive one. What's the square root of 16? 4. Square root of 4 over 25? 2 over 5. All right, here's a hard one. Square root of 0.04. Now, we would like to say 0.02, but let's review multiplying by digits. If I were to multiply this out, 2 times 2 is 4, 0, and then you would come in and have 0. How many decimals are you having here? Because I have 4 decimals there. How many decimals is your answer? 4. Okay, that's not going to work. So it's not 0.02, 0.2, because if I have 0.2 times 0.2, then I would have my 4, my 0, and I have 2 decimals, and yay, I'm happy with that, okay? So just be a little careful with your decimal world when you're doing it. You could also think of this as the square root of 4 over what? 100. And what's the square root of 4 over 100? 2 over 10. Oh, yeah, there's where the 0.2 is coming from. All right? So just be careful with decimals. And then over here, negative square root of 169. Negative 13. Hey, the 13 is the principal one, and I indicated I wanted the negative one by sticking the negative in front to tell you I wanted the negative root. Okay? All right, everybody good? Easy, right? Perfect squares. What do we say when we get here? Square root of negative 9. Is that a real number? Oh, no, yeah, there was this whole discussion that you said you probably just went, you can't take the square root of a negative. Well, you can take the square root of a negative, but when I do take the square root of a negative, I do not get back a Real number. What do I actually get back? An imaginary number, which we will save for another conversation, because right now we are living in real world, okay? We will leave these imaginary little number things as a discussion for 0.7, which is going to be the next section. But for right now, we would simply say, and what do I, when the result is not real, what do I say? Undefined. What was the other time that we had a result that was not real? When you have division by 0. Oh, yeah. Okay, so here's case number 2. Anytime that I have, leading up to my algebraic expressions and my domain and my restrictions, right? Anytime I have an algebraic expression that has a square root in it, if I were to plug in a negative number, it would result in not a real number, which would mean that it is a restriction, right? Just like division by 0 is considered bad, doesn't return a real number. We're going to have square roots of negatives are going to return restrictions, which would be things that we're going to throw out of the domain, and so we're going to have the same conversation we had with the last section. Except now we have to maybe throw out a lot more than just one number. We're going to throw out a whole bunch. We'll come to that in a second. So in all of these cases, right now, because we live in real world, it doesn't matter that those are nice 9's a perfect square, 100's a perfect square. Doesn't matter, okay? All that matters is, hey, it was negative and that is not a real number. So we say undefined in all of those cases. You will never, and I should walk around and look at your paper, but did anybody put the little null set symbol there? Because you shouldn't. Because null set is a set that is empty, and I'm trying to say that this evaluates to not a real number, which means it's undefined over reals. Okay? So your only choices here are to simply say not a real number or to say undefined. That's it. Those are your only answers that you're allowed on that. Okay? Now, properties of square roots. You're probably used to seeing these ones where they're, what if they're not a perfect square? Okay? Like I want to do the square root of 45. What do you really think of 45 as? 9 times 5. You basically figure out what perfect square divides into it. And then now let's talk about square roots. Square roots, once I start splitting this off here, remember we changed to GEMDAS? Why did we change to GEMDAS? Because G stands for grouping, okay? And so when we are doing these radicals, just like the top of a fraction, the numerator is grouped together, even though I don't put parentheses there, it's grouped. The denominator is grouped. If I have a radical, the radicand is a group. It is understood that whatever is underneath the radical, whether I write it or not, technically has parentheses around. Okay, so it's understood to be there. And square roots, what could I write a square root as that we've already talked about? A power of 1/2. So it's an exponent. Okay? So now in this situation, you go, hey, square roots are exponents, right? They're exponents. They are something to the 1/2. Can you distribute exponents over multiplication? Yes, you can. When I look at this problem, I can split it to square root of 9 times square root of 5 because I know that I can distribute over multiplication. Exponents distribute over multiplication. And then we were allowed to get our final answer, which was, what is the square root of 9? 3. And then square root of 5, we would leave it like that. Now, coming back and talking about classifying. If you were to classify square root of 16, what kind of a number is square root of 16? Your choices are you got real, rational, irrational, integer whole, natural, all that. Name what square root of 16 is. It's a natural number, also known as, can I call it something else? It's a whole number. It's an integer. It's a rational number. Doesn't matter that there's a radical there. It's not irrational because the square root of 16 simplifies down to 4. So it's a rational number because I can write it as 4 over 1. And then it's a real number. Okay, so we can kind of walk our way through it. Just because you have a radical does not make something irrational. It's only if it doesn't simplify to a nicer number. Okay? That's like if I gave you 10 over 5 and I said, well, is 10 over 5 not an integer? It's a fraction. Would that make it not an integer? No, because 10 over 5 reduces to 2. So it actually is an integer. So you want to get to the smallest thing that you can look at. But now down here, could I simplify out the radical? Do you know the square root of 5? What do we know about this if we were to type it in our calculator? What would the calculator give us? Between 2 and 3, a decimal that is not terminating and not repeating. Okay, so we can estimate that. And so the idea here is we have an irrational number. Let's look at square root of 96. What perfect square can I divide from 96? Yes, Santosh. 16. Okay, and what is it? 16 times, 6. Now what if you couldn't see that? Okay, maybe I don't have all my prime numbers all in my head that I can divide easily. Do y'all remember doing factor trees in like Algebra 1? Name a prime number that divides into 96. 2 or 3? Let's go with 2. 2 goes in, how many times? 2 goes into 9? 4, with 1 left over. 2 goes into 16? 8. Okay, now 2 times 48. What's 48? Name a prime number that goes into 48. 2, 2 and 24. Name a prime number that goes into 24. 2 and 12. Name another prime number. See, we just keep going. 2 and 6. Name another prime number. 2 and 3. Are we done? Because now 3 is prime. And then we go, all right, we have 2 times 2. Another pair of 2's. That would be 4. 4 times 4 is 16. That's where I'm getting the 16, right? That's my perfect squares, pairs. And then what's left over? 2 and 3, which is my 6, the non-perfect square. Okay, so I can use a factor tree if I have trouble with big numbers. And then from here, what's my final answer? Square root of 6. Notice that we don't necessarily rewrite this into this separate. We just do it because we know we can. We're like, hey, I can just take the square root of each one individually and distribute it and get my answer, and I'm good. All right, what about square root of negative 32? Undefined, right? Because square roots of negatives do not return real numbers, so they are undefined over the reals. All right, so now we come down here. Now we're getting out of number land. Okay, right? Hey, let's make these algebraic expressions. And since we have some numbers that we plug in for x will return real numbers, and some numbers we plug in for x will return non-real numbers, we have restrictions, and we have a domain. Okay, we are also going to have exceptions, but I'm not going to talk about that yet. I'm just going to get the restrictions and the domain down. All right, so reminder, your restrictions are any number that causes the expression to be undefined. Okay, and our domain is all the numbers that we're keeping that make it defined that turn into a real number. So we take the reals minus the restrictions, and we end up with our domain. Now, in the fraction world, we're only really throwing out, when we take out the restrictions, usually they were only like 1 or 2 or 3 of them, because only a finite number of values would make the denominator equal to 0. But what's true about our restrictions here? How many restrictions are there for square root of x? And there's infinitely many of them, because what numbers am I not allowed to plug in for x? Negative numbers. So my restrictions are any x real number that make the radicand, so I'm doing general first, the radicand less than 0. So for this problem, what's the radicand? X. And so what real numbers make x less than 0? Well, x less than 0. But we usually like to describe this, since it's a whole set of numbers, not just a few, and it's a whole interval of numbers, what would be a good notation to write this as? I wouldn't even go set builder. What do you do? Intervals of real numbers. Interval notation, right? Hey, so we're really looking at the restrictions in this problem. So now I'll come over here. That was my general statement. My restrictions would be negative infinity to 0. Right? Any number that I pick in that interval is going to cause this to be undefined. So then what's my domain? How do we do the domain? Domain is reals minus the restrictions. Okay, but we're never going to leave it like that because we're going to be like, oh, hey, if I take the reals and I take out the negatives, what's left? 0 and positives, right? So bracket 0 to infinity, and this is how we do our domain. The reals minus the negatives, that's what we're doing in our head. You don't really need to write that part down. You're going to say, hey, I know the domain, take the reals, subtract out any restrictions. What's left? Always give me the interval that is left. Okay? Everybody good? All right, let's look at the next example. So now in the next example, our radicand, what's our radicand? X minus 2. So whenever x minus 2 is negative, that's going to give me restrictions. When is x minus 2 negative? What do we know about x when x minus 2 is negative? 2 or, is it equal to 2? Less than 2. There's no equals right there. So less, all I'm doing is just adding 2 to that side and say, well, when is x minus 2 the radicand negative? The radicand is negative specifically when x is less than 2. So my restrictions would be negative infinity to 2. These are all the values that give me a negative under the radical, which are going to cause me to return not a real number. Okay? What's my domain in this problem then? My domain. 2 to infinity. What should I put with this 2? The little bracket, right? To infinity. Because reals minus everything less than 2 means I keep 2 and everything above. Right? See, it's not hard, right? Domain is actually pretty easy for these, for the most part, until we get farther out. All right, so here again, I'm going to do my restrictions. My radicand is 3 minus 2x. And whenever that radicand is negative, it's going to cause me a problem. All right, let's review a little inequality solving from Algebra 1. I'm going to subtract 3 over. And then what do we want to do? Divide by negative 2. And do y'all remember something about that? You got to flip the sign. So x is greater than negative 3 over negative 2, which is 3/2. So my restrictions in this problem, based on this work, are going to be parentheses 3/2 to infinity, because it's x greater than 3/2 of the problems. And if that's my restrictions, what is my domain? What's left after I throw away these restrictions from the real numbers? Think of it like, what's the opposite of being bigger than 3/2? Less than or equal to, so negative infinity to 3/2 with a bracket. Right. Square root of x squared. Do my restrictions. My radicand is x squared, and whenever that is negative, that's going to cause me to not have a real number. Comments? Any value that I can plug in to x that will make x squared negative? Any real number that I can plug into x squared that's going to make it negative? Any real number? Yeah, there aren't any, right? If I take a negative number and I square it, I get a positive. If I put in 0, I square it, I get 0, not a negative number. And if I put in a positive number squared, I get a positive. So what does that tell me about restrictions? There are none. No restrictions. What does that tell me about my domain? All real numbers. I didn't subtract anything out. There weren't any restrictions in that case. Just because you have a radical doesn't mean you have restrictions. You're looking to see whether the radicand itself is positive or negative. All right, now let's up the ante a little bit. I have two variables in there, an x and a y. All right, so let's look at our restrictions. Our radicand is now 6x cubed y squared. And whenever that radicand is negative, I'm going to have a problem. Now, can somebody tell me if I can reduce this down a little bit? What do I know about 16? 16 is always, well, it's 4 squared, but it's always positive, right? Does that really affect whether, if I have the product of three different things together, I'm trying to figure out when the product is negative? This 16 is always positive. Is that really going to turn it into a negative number? No. What about y squared? That's always a positive number too. Those two factors have no bearing on whether the product is negative because they're always positive. So in this problem, I can narrow it down and say, well, pretty much y can be anything it wants to be, right? Is everybody okay with that? All right, so over here, we're going to have to do this as set builder because I have two variables. So my domain, the set of x, y, such that right now we know y is a real number. It can be anything it wants to be. Because y squared is always positive. But this x cubed, would you agree that the product, 16x cubed y squared, would be negative exactly when x squared or x cubed is negative? Right? And when is x cubed a negative number? When x is negative. Okay? So we need to make sure that our restrictions are x is negative. What would x have to be in order to be in the domain? What's the opposite of being less than 0? More than or equal to 0. So we would say and x has to be greater than or equal to 0. So you have to do your quote-unquote domain. What am I allowed to plug in? By doing set builder, because you got to tell me what's the y, what's the x. All right, now let's look at this one. Very similar, but a little different. All right, so now we have restrictions. I have 16x cubed y is my radicand, and whenever that is negative, that's going to cause me to not have a real number. So now let's look at this. Does the 16 have any bearing on being negative? No, so I can pretty much ignore that. But this x cubed y, all right, let's think about when would x cubed y be negative? What are my cases, my scenarios? If x is negative and y is positive, right? Or I could have x positive and y negative. So everybody kind of, I'm reasoning out my choices here, okay? So my restrictions would be, and this is hard to write, so usually you just kind of put it in English now. If x is less than 0 and y is greater than or greater than 0, if x is less than 0 and y is greater than 0, then my 16x cubed y is negative, which is why it's a restriction. But that's only case 1. Case 1. Case 2, if x is positive and y is negative, then 16x cubed y is negative again. What happens when they are both positive? Then we're okay, because positive times positive is positive, and that would work and give me a real number. And if they were both negative, that would be okay, because what's a negative times a negative? Positive. And remember, because these are grouped under the radical in order of operations, I would actually multiply first, and then I would take the square root, and so the multiply happens, everything turns positive. So it's only a restriction if they're one positive and one negative. So now let's do the domain. Let's come over here, right our rail. So domain would be the cases that we have left. What are the cases I have left? Either they are both positive or both negative. That's when I want to keep them. Okay, so we would do set builder, set of all x, y, such that, now we do cheat a little bit in here. If I want them to both be positive or both be negative, can I get that with one statement? Can I just go, when the product x times y is greater than 0, would that be enough instead of having to write all the English words? Is that okay? I could have, like over here, instead of writing this, couldn't I have just said, oh, hey, when x times y is negative? And when would that happen? Exactly when one or the other is negative. So you can kind of boil down the words into one statement. Because remember, in set builder, you just have to have one rule that everybody can follow to make sure you're in the set or not. So if I were to say, okay, if I want to pick 5 and 7, 5 for x, 7 for y, can I plug that in? Will that give me a real number back? But what if I picked 5 and negative 7? Would that work? No, because you're like, hey, that's not in that set because 5 times negative 7 is not positive, so it gets thrown out. Right? Good? All right, so that's restrictions and domain. All right, now let's come down here to the next little part here. There's a few issues with simplifying radicals, okay? And we have glossed over them to this point. In the exponent section, even though I was throwing a couple of radicals in there, I always told you that everything that you were taking the square root of or the cube root of was positive. I don't know, you probably didn't notice that. I kind of slid it in as a little, hey, these are positive numbers. And the reason why I did that is because I did not want to have a discussion about the weird little exception thing that happens in square roots back in section 0.2. I didn't want to have that discussion yet. So I cheated, and I just didn't tell you I cheated. And your Algebra 1 teachers have been cheating all along because they have been always giving you these little problems to work with. And they have always said, hey, we're just going to let x and y be positive because then there's no problems. But now that we're in Algebra 2, it's time to pony up and say, hey, I now have to figure out when I have exceptions. It's kind of like the whole division by 0 thing. You didn't really address division by 0 in Algebra 1. We're going to address square roots of negatives here. So let's take a look at this. Order of operations. What is this one telling me to do first? Square 3. So 3 squared is 9. All right, order of operations. Square root of 9, 3. Okay, we're like, all right, I understand how order of operations works. Let's take a look at this one. Order of operations. What do I do first? Square negative 3, which is? And I get 3. Same answer I got in the first one. However, what if I had this? Yeah, what happens first here? What do I actually square first? Just the 3, right? Because order of operations says do the exponent before you multiply. That caught you on the quiz a little bit. Let's not let it catch you again. And the square root of negative 9 is undefined. So these pesky little parentheses matter a lot when you have these negatives. What about this one? Order of operations. What should I do first? Square the 3. So I have negative square root of 9. And then what's that? Negative 3. Why did that end up being negative? Because they were telling me they wanted the negative root by putting the negative in front of the principal root. All right, is everybody good? Now, specifically, the big idea comes from these two. I'm going to put a star by them, put an arrow to this. Because now we want to go to an algebraic expression. An algebraic expression. So instead of thinking of this as a specific number, I'm going to start thinking of that like a variable. I'm going to either plug in a number, and that number is going to be positive, or that number is going to be negative. If I have it in this order where I square first and then I take the square root, what did we notice about the type of number we got back both times? It's the same number and it happens to be positive. Even if I put in a negative number for the value, because of order of operations, because the first thing you did was square it, it actually ended up being a positive number both times. Okay? So this is always positive, even if a is less than 0. Okay? if I was going to talk about the domain, which I did earlier, what was the domain of the square root of x squared? What was the domain? We just did it in the previous section. What was the domain of the square root of x squared? All real numbers. I can plug anything I want into this, and I always get a real number back. Why? Because the first thing you do is you square it, which makes it positive, so it's always defined. So then the question is, I need to designate that. I can't just say square root of a squared is a. All right, does everybody see why that's a problem? Because if it was -3, then that's not correct. Do we have a function that you looked at in Algebra 1 that always makes stuff positive? Oh yeah, so there we go. That's big idea number 1. Anytime you are simplifying, okay? Anytime you are simplifying, and if I see the square root of x squared in my work, I am not going to go, hey, that's going to be x, because I'm going to remember this discussion and say, no, that really is going to be the absolute value of x, that it has to be a positive number. Another clue to remind you is because this is the principal root, and the principal root is always which one? The positive one, so it has to return a positive value. Now, one last thing and then I'll let you go. This is what we call a piecewise function. Piecewise. Because really there's two things going on, depending on what x is. And hopefully you've seen this in Algebra 1 before. But if x is 0 or positive, does this absolute value bars do anything? No. So we go, hey, that's x if x is greater than or equal to 0. When x is positive or 0, I don't do anything. But if x is less than 0, what do I have to do to the number to make it positive? What would be a way to make it positive? What operation could I do? Multiply by -1. So I could take the opposite of what x was, the opposite of a negative number, and that would turn into a positive number. Okay? So we'll stop there. Okay, so basically what we've learned from this big idea here is that the square root of a squared, when the square is underneath of the absolute value, we need to remember that that is the principal root, which is always positive. And when that is always positive, we need to remember that despite what x is, whether x is positive, negative, or 0, because 0 will work as well according to this definition, that what we want to return is the absolute value of x. Now this is going to be very important for when you are simplifying. You can't just eliminate, like if I had square root of 3 squared and just say 3, if you have square root of x squared, you are not going to be able to just say x. You're going to have to remember that you need the absolute value of x. Right? So now let's come down here to big idea number 2. Now in big idea number 2, now the order is changed. The exponent is now outside of the square root. So because of the way that the grouping is, we are going to apply the square second after we do the square root. What does it mean when we square a number? It means square root of 3 times square root of 3. Now, because this is positive, we can go ahead and be like, well, that really is the same as square root of 3 squared, which does happen to be 3. So this doesn't change at all. However, over here, if we use the same reasoning, that this is the square root of -3 times the square root of -3, because we have to perform the square root first, in this case it matters. The square root of -3 is actually undefined. So what you learn from just this kind of scenario compared to the previous one is that the square root of x squared is not the same in every case as the square root of x squared. Okay? So we have two things going on, that when we are doing these even radicals, these square roots, that we're going to have some concerns. That order really matters in this, and we're going to have to pay attention to how we kind of affect this. And then just kind of finishing out, let's go ahead and take these two and go down to the big idea, and then we'll look at the last two order of operations. So if I have the square root of a and then square it afterward, that this is only going to equal a, there's an exception to this. So it's kind of like when we lost the restriction, that what I'm doing when I square a square root, you are removing a restriction. It's very similar to what we did with the fractions, where when I was canceling the denominator factor that was causing a division by zero problem, that was removing the restriction from the denominator. So when I'm canceling the radical in this fashion, then that is removing a restriction. And so when I lose the restriction, I have an exception. So here I have to say where, or let's do the except statement. Let's do our glass half empty statement, okay? Which is basically that we would say A except when x is negative or x is less than 0, okay? And so notice that there's a big thing here. This is huge to recognize that these are not the same thing, that it depends on what you put in the algebraic expressions. So whenever you see the square root of a squared, you're going to put in an absolute value of a, or square root of x squared is absolute value of x when you are simplifying. When you see something along the lines of square root of x times square root of x, you're going to say, well, that's equal to x except when x is negative. Okay? And so that makes simplifying radicals a little bit more difficult and not as straightforward as we would like them to be. Now, with these exceptions, I want to talk about glass half empty, half full, just so that you can see the different ways that you're looking at them. Now, what we've been doing for the fractions, okay, when we had the division by zero problem, we would say that we would have the expression, and then you would say except when x equals, say, 2. And that's a glass half empty. We're basically saying, hey, this is true except for when x equals 2, it's going to be false. Now, but you can say that a different way. You can have your expression, and instead of saying except when, you can simply go when x does not equal 2. The except is like a negation, and so you could say it both ways. They're both perfectly acceptable. I've been stressing this one simply because they're called exceptions, and I was trying to say, hey, this is true except when, hence called an exception. But you'll see a lot of times that what we do is we simply turn it around. Instead of a negated statement, we just go ahead and run the negation through and turn it into a not equals. If I'm doing it with the radicals, all right, when I'm doing it with the radicals, you would simplify your expression. And usually, like the previous examples, I'd say except when x is less than 0. And then you say, well, let's negate that. What is the opposite of x less than 0? In set world, because it's a whole set of values, if you are not negative, then you must be 0 or positive. So you could say glass half full, and you could say simplify your expression, and then just say when x is greater than or equal to 0. So it kind of works both ways there. And we'll take both versions of this. Just kind of pay attention. If you're going to give the exceptions, you say except when, and then give me the places, the x values for which the expression is not true. And then if you're going to turn it into your glass half full version, then you do the expression when x is greater than or equal to 0, when they are true. Okay? So it's kind of two ways of looking at it. All right, now we have another big idea before we actually get into the simplifying. Let's take a look at this. Let's go back to the previous page. I forgot to do those last two. All right, so now coming back here, this is just playing on order of operations. Square root of 3 squared, 3 is positive, so the square and the square root will cancel. So I have negative times 3, and we're done with that problem. Now here, now notice the square did not go to the negative. It was I squared the square root first, and then I multiplied by negative. Order of operations, GEMDAS. Over here, now the negative is inside the parentheses, so just reminding you that that square should distribute to the negative, which makes it negative times negative or positive, and then I square the square root of 3. 3 is positive, so the squares will cancel, and I would end up with positive 3 in that case. So just playing around with order of operations and being careful. All right, so now our third big idea. Square root of 9 times square root of 4. Square root of 9 is 3. Square root of 4 is 2. 3 times 2 is 6. that you can treat this, perform this square root first, perform this square root second, because exponents come before multiply, and then multiply. All right, now here, because we have the square root over the 9 plus 4, remember that square roots are grouping symbols. So there is a understood parentheses here. So we would apply the multiplication first, square root of 36, and square root of 36 is 6. Notice that in this case, they are exactly the same, okay? Square root of 9 times square root of 4, square root of 9 times 4. It did not matter what order I performed that in. But now let's come over here and let's take a look at this next pair. All right? So according to this, again, because of the grouping, we're going to do group negative 9 times 4 would be square root of negative 36, and then bells should go off and we say, wait a minute, that's undefined. Multiply first, take the square root. Now over here, all right, I take the square root first. Well, the square root of negative 9 is undefined times 2, and just for making sure we understand this, undefined times 2 is still undefined. So in this case, again, you're like, yeah, I could distribute the square root over the multiplication, and that worked perfectly fine. Right? So we're going to put that there. Now we're going to come over here and we're going to say, okay, now let's talk about distributing when I have two negatives. Now according to this, I'm grouping the negative 9 and the negative 4 together, so I'm going to perform that first. So that becomes the square root of positive 36, which is 6. So this one is defined. Now over here, because of the order of operations, I have to do the square root of negative 9 first. And you're like, oh, wait a minute, I get undefined times undefined, which is undefined. This case, these are not equal to each other. So we have to be very careful, you know, up until this point, if I had x, y, and I was squaring it, then we went, oh, go ahead, distribute the square through. This would be x squared, y squared, and we never had any concerns over it. Now that we are dealing with these restrictions and exceptions and things like this, what we have to realize is that this is not true in every case. There is one case over here, an exception for when this is going to be true. So when can I distribute a square root over multiplication? I can distribute it in every case when they're both positive, one's positive and one's negative. I cannot distribute it when they are both negative. I will not get the same answer. So this would be equal to the square root of a times the square root of b, except when x is, now we're not doing x's right here, except when a and b are both negative. Okay? So that's our exception to this. We have to be very careful when we have variables about this, because this is going to, when we use it, cause an exception, and so we'll have to pay attention to that. Same thing is true here. Let's just extend it over the division, that this is true except when a and b are both negative. All right, and then one comment before I come down here to simplify and we work with the examples. Just as I probably should have just put a box in here for this, just to remind you, powers do not distribute ever over addition or subtraction. So never tell me that the square root of a plus b, that is never equal to plus or minus square root of a plus or minus square root of b. You cannot distribute ever over addition or subtraction. If I have multiplication, I can distribute as long as both of my terms are not both negative. And I sometimes will go ahead and distribute as long as I note the exception that's going to be there. All right. So now what we're going to do first, okay, so I have this simplifying algebraic expressions. And I've also given you a handout that has this little chart on it. All right, so we're going to start with the first thing, which is we have this original expression. I want you to plug in x equal to negative 1, tell me what you get. Plug in 0, put down what you get. Plug in 1. All right, So you're going to do this first. So that's number 1 in this activity. Okay. Then I want you to come back over to this page, and I want you to try to simplify this. Now, you're going to need to remember that as you are simplifying, there are actually three big ideas. That if I have the square root of x squared, that's an absolute value of x. That if I have the square root of x squared, that's going to equal x except when x is less than 0, so I have an exception. And then the two that we talked about up here, that you can split as long as you're paying attention to that. If both of these have a possibility of being negative, you are creating an exception for that. Okay? So I'm going to let you play around with it first. All right? So what I want you to do is go ahead and give it a try. Try to simplify these. Try to make sure you have absolute value when you should. Try to have your exceptions. And when you get to the end of the problem, right, after you've simplified each one, so you'll simplify number 1, the first one here, then I want you to come back to this page, and I want you to put your simplified expression here, and I want you to plug in -1, 0, and 1. Okay? So this is number 3, step number 3. Step number 2 is simplify. Once you get it simplified and you plug these in, if you do not get the same thing that you got over here, I need you to go back and revisit the big ideas and think about, did you miss an absolute value? Did you miss an exception that you needed to put in? And usually that should catch you on any time you have forgotten one of these. Okay? So you're going to go through, do this for each one of these, and then we'll come back together and I will restart the video. So I'm going to pause the video and let you guys work for a little bit, and then I will come back and we'll talk about each one individually. Okay, so now coming back, let's just kind of walk our way through like this first one, just to kind of make sure that we're on the right track. First thing I recognize, I have 48 and x squared. Both of those are positive. So it's not going to be any difference to me if I split this into square root of 48, square root of x squared. Right? Because they're both positive. Don't have to worry about anything. There's no exceptions. Square root of 48, you have to pull out your perfect square. Remember that 48 is going to be 16 times 3. So that's the square root of 16 times 3. Now we can go ahead and start simplifying this. Square root of x squared, big idea. That's absolute value of x. Okay. Then when you come and you look at this, square root of 16 is 4. So we now have 4, square root of 3, and absolute value of x. Now I am going to add something in. I probably should have said this in the instructions. But I also really should think that you should always do domain and restrictions before you simplify. So let's come back over here to the beginning and let's talk about domain and restrictions. We know that the restrictions are going to occur when 48x squared, your radicand, is less than 0. Okay, so those are my restrictions. When does that happen? And in this case, hopefully you'll go, wait a minute, 48 is positive, x squared is positive. This never happens. So there are no restrictions. So in this problem, the domain is -infinity to infinity. Right? If I were to look at this, I want to make sure, can I plug in positives and negatives over here and 0, and I'm fine. Now, what I want to do is let's do the test on our little part here. If I were to plug in -1, okay, and plugging in -1, we would simply have -1 squared, which is 1. 1 times 48 is 48, square root of 48, which is our 4 square root of 3. If I plug in 0, I get square root of 0, 0. If I plug in 1, I get square root of 48, which is 4 square root of 3. And notice that we said the domain was -infinity to infinity. So therefore, we were able to plug in a negative number, a 0, and a positive number, and I got answers. I got real results every single time. All right. Now, we simplified this to 4 square root of 3 absolute value of x. Now I'm going to plug in negative 1. Negative 1, absolute value is 1. 1 times 4 square root of 3 is 4 square root of 3. And notice we got the same answer in both cases. Now, do you see why you need this absolute value here? That without this absolute value, this answer would not be the same, because I would have negative times 4 square root of 3. I would get a negative result. You want to make sure that you are seeing the big idea, because you're trying to make sure your simplified expression gives you the same answer. All right, now we're going to plug in x equal to 0. Okay, that's easy. Absolute value of 0 is 0. 0 times anything is 0. Right? So that's not a concern. And then plugging in 1, you're still okay. All right? So the idea here is that the reason that we have the square root of x squared as absolute value of x, that's because when x is negative, you have to remember you squared it first, made it positive, and then took the principal root, which means it always had to return a positive result. And that's why we have that absolute value there. All right, let's come back to the second one. All right, I'm going to do the domain first. Now when I do my restrictions, I have 28x cubed less than 0. And that can be negative. That's negative when x cubed is less than 0, which would be negative exactly when x is negative, because a negative times a negative times a negative is positive. All right? So our domain, if we're throwing away all the negatives, our domain would be 0 to infinity. Before I simplify, if we go over and we plug in our values, our negative 1, plug in negative 1 here, you end up with negative 1, negative 28. Square root of negative 28 is undefined, okay? Which should match, because remember, we'll bring our domain over, 0 to infinity. Now I plug in 0. 0 is going to give me 0. That works. I plug in 1. I get square root of 28. What is the square root of 28? I believe that's 7 times 4. So 2 square root of 7. Right. Now let's simplify. Okay, I want to simplify this, and we already did the hard work. Now, this is okay to split because they're not both negative. 28 is a positive number. So I can split it to square root of 28, square root of x cubed. Square root of 28, we just did, is going to be 2 square root of 7. Now the square root of x cubed, I'm actually going to rewrite that as the square root of x squared times x. Now by doing that, I have something that's positive and something that's negative. So they're not both negative. So I actually can split this out. 2 square root of 7 square root of x squared times the square root of x. Now I see my big idea. This is going to be 2 square root of 7, absolute value of x, square root of x. Now I'm going to pause here and let's talk. This would be a perfectly correct answer. Okay? However, when we are simplifying, we're trying to go for the simplest version possible. And what we need to recognize here is that, remember, our domain in this case was 0 to infinity. And I still have a square root over here, so I don't have any exceptions. I haven't lost my restriction. My restriction is still there. If I were to plug negative 1 in right here, I'm going to get undefined. I don't need this absolute value anymore to make the principal root positive, because the only thing I'm allowed to plug in is a negative number. So it's almost unnecessary to have the absolute value in this case, because I can't plug in negative numbers anyway. They don't return real results because of the restriction on the square root. So because we're going for the simplest version possible, we will go ahead, even though we know the big idea, like, hey, we already took care of the negatives, they're going to be undefined, we will rewrite this as x square root of x. Okay. So now we come back over to our explanation over here. We're going to put our simplified version, 2 square root of 7 x square root of x, and then just to prove to you that this works, I plug in negative 1. Square root of negative 1 is undefined regardless of what I have over here, so I am undefined. That's why I don't need the absolute value. Okay, I'm not going to get an answer here. It's going to be undefined. It's not real, so I don't worry about it. Now, I will caution you that if I was in complex world, that absolute value would be important. But because I'm in real world, we can simplify farther. If I plug in 0, 0 times anything is 0. Plug in 1, we get 2 square root of 7. And again, we see that we got the check, and everything is good all the way across. All right, so now let's take a look at the third one. All right, in the third one, we have 12x, 6x. Now, because they're not both negative, I am going to go ahead and split this up. I'm actually going to regroup. Okay, let's talk about the domain. All right, so now we're taking a look at this product right here. Now, what we can do with the numbers is we can group the numbers together because they're positive. So just like you can split if they're both positive, you can put them together. So I'm going to regroup this as 12 times 6, and I'll address how to simplify that in a moment. And then I have a square root of x times the square root of x. All right, so now when we look at this, the numbers, I can look for my perfect squares, and really you have 4 times 3 times 3 times 2, and really so you end up with 4 and 9, which is 36 times 2. All right, so that's going to allow me to pull out a 6. And then this is that square root of x squared. Notice I did not put these together as the square root and make it x squared underneath. I have to recognize that this is different. It's order of operations, that it really means this. So now when I go to simplify, I have 6 square root of 2, and this simplifies to x, but it has that exception, except when x is negative. If we come back and we think about our domain, because of the order of operations, because I have the square root of 12x, that would be negative when x is negative. So my domain is going to be 0 to infinity. I throw away the negative x values. When I get over to here, I want to make sure I'm still throwing away the negative x values. I am losing the restriction from the radical by squaring it in this order, so I have an exception. Now, we take a look at this one. Now, this one you want to be careful because in order of operations, remember that we have this grouped together under the radical. So we should actually do the simplifying inside first. So same thing that we did before. I'm going to make it 36 times 2, because that's going to be the same. And then it's going to be x squared. So I get a different scenario than what I had above because of the order of operations. The domain in this case is going to be negative infinity to infinity because x is squared under the radical, which means it's never negative. So there are no restrictions, and the domain is negative infinity to infinity.
Chelsea Motley, report to attendance. Chelsea Motley, report to attendance.
All right, so now I can take the square root of 36 is 6. The square root of 2 is square root of 2, doesn't simplify. And the square root of x squared is where you have to remember, big idea number 1 is going to return absolute value of x. Okay? Now, x can be positive or negative, so I cannot simplify this out and remove the absolute value, so I'm pretty much done with the problem. All right? And that's as far as we can go. All right, let's take a look at this division over here. Now, again, we have that order of operations. Now, I'm going to split the top. I can do square root of 45 times square root of x cubed, because they're not both negative. I can bring out the square root of 5 and the square root of x, because they're not both negative. Now, because these numbers are both positive, not only can I split things when they're positive, I can put them together. I'm going to treat that as the square root of 45 over 5. Okay. Now here I want to be careful, because it's possible that both of these could be negative. So I'm not going to put these together. I'm not going to do the same thing I did with the numbers. What I'm going to do instead is now I'm going to split x cubed into the square root of x squared and x, because x squared and x, they're not both negative. All right? And when I split it like that, what you notice is, oh, I can remove the square root of x. So that's how I'm going to work on my simplifying. I'm going to recognize that I can cancel those out. Now, if we keep going with our simplification, this is going to be 45 over 5, which is the square root of 9. And then the square root of x squared is going to give me my absolute value of x. And now we have to worry about domain and exceptions. So we come back over here and let's take a look at the original problem. Since x is under the radical and even x cubed, our domain, hopefully you're starting to see kind of the pattern to this, that the domain would be 0 to infinity.
Colin Mitzimer, Elizabeth Hayes, report to room 100. Colin Mitzimer, Elizabeth Hayes, report to room 100.
All right, so we do have restrictions on this problem. And notice that when I come over here, that by removing this division by 0 problem and removing this radical, I have essentially caused myself to have a exception, okay? And the other thing is to notice that I'm going to put the exception in, which is I need to make sure that the negatives give me undefined. So we're going to say except when x is less than 0. And as soon as I throw out the negatives, then I get to go one more step. Square root of 9 is 3. I no longer need the absolute value because I've thrown out the negatives. That's going to be undefined, so I'm only allowing x to be 0 or positive, which means I know that the absolute value of a 0 or positive is simply going to return x because I have this exception written. And so that's going to be our final answer for this problem. All right, now let's look at the final question and take a look at where I have the division under the radical. So order of operations, we are grouped together under the radical. So I'm going to take the square root and I'm going to simplify in here. So we have our 9 and then x squared. Now notice if I think about the domain here, that you want to be very careful here. Not x can be positive, x can be negative because you would have two negatives and it would divide out and become positive, but we cannot have x equal to 0. We have a division by 0 problem. So my domain is negative infinity to 0, 0 to infinity. Okay. And then let's continue our simplifying. So I have square root of 9, square root of x squared, 3, absolute value of x. And I do have an exception. I'm okay with the negatives and the positives, but I have to say except where x is equal to 0. I have to throw that one out. All right, so this will give you a good explanation of your domain and then simplifying radicals and dealing with restrictions, domain, and exceptions.